All okay, all right. All right, good evening, everyone. So, we're going to start our lesson for specific latent heat today. Okay, so, let's see. The notes that I'm having right now is actually the notes from the textbook. I copied and pasted into the PowerPoint so it's easier for me to explain. All right, if I really need it, then I will convert it to uh, the I will go over to the PDF files, but I'll let you guys know. Okay. So in terms of specific lesson heat, I think the textbook notes are actually quite complete and quite compact. Okay, so let's start. I want to change the color first. Okay. So previously we talked about specific heat capacity. All right, where specific heat capacity is the amount of heat required or absorbed or released, right, for 1 kg of substance to change the temperature of 1 degree Celsius. But latent heat, right, over here do also identify that there's a difference here. Same thing as heat capacity and specific heat capacity, we need to learn two terms right now: specific latent heat and latent heat alone. All right. So elements exist in three states. We have the solid, we have the liquid, and the gas state. So the difference in the arrangement is that solid is more closely packed. All right. It vibrates at its own position. Liquid is slightly more loose. All right. It's still packed, but it's much more loose. Okay. And then gas is randomly moving all over the place. All right. The bonds between the gas molecules is very, very weak. Okay. So over here in latent heat, we talk about the phase change. All right. Phase change means from solid to liquid, from liquid to gas, or from gas to liquid, and then liquid to solid. Okay. So in a way you have learned it a little bit in chemistry, okay, but what you learn in chemistry, what we emphasize in chemistry and what we emphasize in physics is slightly different. All right, so please do take note, don't confuse yourself when you explain the stuff. Okay, so during changes of phase of matter, such as the boiling point and melting point, the temperature will remain constant even though the heat is being supplied is continuous. Okay, so first thing first, right? What is latent heat? So for those form fours who's having your textbook, please underline or highlight this. All right. Form five. All right. So you have finished your trials already. So right now, please take this as a revision. Write down back again. All right. Latent heat is the heat that is being absorbed or released during melting and boiling point. Keyword: without change in temperature. All right. So for latent heat, the heat energy is being absorbed or released during a specific point. All right. But the temperature does not change. So that is latent heat. So during condensation and freezing, all right, latent heat is released without the temperature change. Melting point is where the temperature increase. When the temperature increase, energy is being absorbed. When the temperature is being reduced, all right, energy is being released out. Okay, so that is what we learned in the early part of heat chapter. Okay, so here what we have, the phase change. Okay, this is talking about water. Okay, so when we have solid, all right, when heat is being absorbed, all right, when latent heat is being absorbed, it will melt at melting point, which in the case of ice and water, it would be at 0 degrees Celsius. So heat is being absorbed when the solid melts to liquid, and then when liquid boils to gas at 100 degrees Celsius, all right, the latent heat is being absorbed. So when the temperature increases, energy is being absorbed. Okay, and then when gas goes to liquid, okay, during condensation, all right, also at 100 degrees Celsius, during condensation, the latent heat is being released out. Okay, and then from liquid to solid at freezing points, which also at 0 degrees Celsius, the latent heat is also being released. So this is something that you've learned in science previously. So what we are going to look into right now in form 4 physics is we're going to go into the molecular structures, what happens all this. Okay, so specific latent heat. Okay, I didn't really go and copy and paste very nicely, so the wordings is a little bit blur. All right. So the specific latent heat, as most of you have already noticed, the word specific here is actually means that you have to write 1 kg inside the sentence. So specific latent heat is the sub of a substance is the quantity of heat that is being absorbed or released during a phase change. Okay? For 1 kg of substance without any change in temperature. All right. So, which means that the word specific means that you have to mention it's a 1 kg substance. Okay. That will not change its temperature when it's changing from solid to liquid, liquid to gas, gas to liquid, or liquid to solid. All right. So, that is the specific latent heat. Okay. So, let me show you a little simulations over here. Okay, so over here what I have is over here the top part, you can actually ignore this part for the moment right now. Okay, so let's just say inside this beaker right now we have ice, right? It's fully ice right now because here you see at this position is 0 degrees Celsius and 100 degrees Celsius. So 0 degrees Celsius is the melting point, at 100 degrees Celsius is our boiling point. So what I want you to see right now is this on the top right hand side corner, it actually shows you the heat. This is MC theta. So this is actually the heat absorbed during the change in temperature. Okay, so C is the specific heat capacity. They directly calculate the energy out for you. All right, so let's see what happens when I increase. When I press this green color button, this is a heating pot, all right, a heating plate. Induction cooker also can be considered. So the minute I press the green button, it will actually heat up this beaker of ice. So once I start that, okay, you can see that the energy just now, once the minute I started this one, the energy has already increased. Now over here, what happens is, okay, so I need to increase a little bit. All right, when I press this yellow, I'm making it go slower. I'm increasing the temperature. You would notice the black and also the white color line over here. When I press the yellow button, it actually increases the temperature. So when it increases the temperature, the amount of heat that is being absorbed increases. And the minute I reaches 0 degrees Celsius, you will notice that another line of calculation comes out. This is actually the latent heat that is being absorbed right now. But what happens if you look at this part, you will notice that there's 2 layers of items here already. So I'm going to restart that for you to see. Right now you can see all of this is actually ice. Okay, so the minute I start pressing on the yellow button, temperature increases, energy is being absorbed. But the minute it reaches 0 degrees Celsius, all right, here there's a double layer right now. So I'm going to continue pressing here. You would see that here, all right, inside the beaker, there's still a little bit of ice and there's water. But the temperature still remain at 0 degrees Celsius. Heat is still being absorbed, all right, by the ice and also by the water right now. But at this part, the energy that is being absorbed from the induction cooker, let's just say this is the induction cooker here. So the heat is being released by the electrical energy, all right? It's being absorbed by the water and the ice, but the temperature doesn't change. It still remains at 0 degrees Celsius. So this is the heat that we're talking about, the latent heat that we are talking about actually. So I continue on pressing this to increase the amount of heat that is being absorbed. Okay, I'm going to press the green one to make it a little bit faster. All right, so you can see the ice is actually melting, all right, but the quantity of water is increasing. So over here, there's still a little bit of ice, but the temperature is still remaining at 0 degrees Celsius. All right, the minute all the ice melted, the temperature will start to change. All right, I repeat, when all the ice have fully melted, the temperature starts to change. All right, so here you would see that the third formula comes out. This formula is actually the heat capacity. All right, so I'm going to continue increasing it. That's water being heated up right now. It's going up to 50, 60 degrees Celsius, 70, 80, 90, Now that's 100 degrees Celsius. So the minute 100 degrees Celsius, the latent heat comes out. Okay, so I'm going to continue heating it up, and that is when you start seeing bubbles. Okay, when we start seeing bubbles, this is the boiling point. At the boiling point, water and gas vapor exist at the same time. All right, at the same temperature, water and gas actually exist at the same timing. So if I continue to boil it, you will notice that this takes a very, very long time. Why? There's a lot of water that needs to be boiled and to change to vapor. All right, so it will continue on until all the water has fully become vapor. All right, so at this position, it's going to be more than 100 degrees Celsius already. When all the water has already changed, all right, has fully changed to become vapor, that is already more than 100 degrees Celsius. So when the water is still boiling, the temperature is actually fixed at 100 degrees Celsius. Okay, so this is a simulation of what usually happens. We're gonna go into we're gonna look into what actually happens inside in terms of the molecules. All right. So before that, since the textbook come out with the formula first, we'll look into the formula. Okay. Are you all okay so far? Yeah, because I cannot see your reaction, so I have no idea whether you're okay or not okay one ah. So I memang mind shock sendiri during online class ah. Everyone's so okay then okay lah. Right now I have 44 people. Okay. All right. So let's continue. Now, in terms of formula, all right. Specific latent heat, the formula is quantity of heat. So Q is at the top, is being absorbed or released during a phase change of 1 kg substance. So that's the reason why specific latent heat symbol L is actually the amount of heat per kg per mass. All right, so the mass is actually at the bottom part here. Okay, so if I were to rearrange this formula, I will arrange it to become Q equals to ml. Why? Because we seldom memorize a formula with over this kind of terms. We always memorize the formula as Q equals to M multiplied by L, where M is the mass, L is actually the specific latent heat. All right. Later on, I'll tell you and I'll teach you guys how to use when to use MC theta, when to use ML. Okay. Now the unit for specific latent heat, all right, because it's heat energy, so that's joule, and then mass unit is actually kg. So the unit for specific latent heat is joule per kg. Okay, so that is the formula for specific latent heat. There's two types of specific latent heat. All right, one is for fusion, the other one's for vaporization. Again, Form 4, this is in your textbook. Okay, Form 5, hopefully you have the soft copy of it. Now, specific latent heat of fusion. Fusion is actually when, all right, the amount of heat that is being absorbed or released during melting, or the quantity of heat that is being released during freezing. So you have to be careful what the question asks for. If the question asks general, define specific latent heat of fusion, then you have to make sure that when you say the quantity of heat that is being absorbed, it is during melting, because melting is actually from solid to liquid. All right. If you use the word quantity of heat being released during freezing, all right, because freezing is actually from liquid to solid. Okay, so please be clear. Fusion, if you're going to use the word absorb, it must be during melting. If you're going to use the word release, it is during freezing point. Because of the word specific, we have to mention the 1 kg, all right, of substance without any change in temperature. So the word any change in temperature is also a key point. So please be clarified with this. All right, so Form 5 who is over here, you would know that your trials came out specific heat capacity. But because of the word specific, I need to see the 1 kg word inside your definition. All right. So next, specific latent heat of vaporization. So vaporization will give you guys a clue that vaporization is during the vapor from liquid to gas state. So quantity of heat that is being absorbed, All right, absorb means that the temperature is being increased, so that is during boiling point. All right, or the quantity of heat that is being released. Release means that temperature is being cooled down. So cooling down is from gas to liquid. So that's during condensation. Okay, and again, because of the word specific, you have to mention 1 kg of substance without any change of temperature. So you would notice one thing, the difference between specific heat capacity. Specific heat capacity has two numbers there, 1 kg, 1 degree Celsius. Alright, so specific latent heat. Specific latent heat is whereby it changes its phase, alright, changes its state of matter, which means from solid to liquid, liquid to gas. Alright, I saw let me finish explaining here first, Tongzhen. So, for specific latent heat, I only need to see the number of 1 kg, but without any change in temperature. Heat capacity, specific heat capacity must change the temperature by 1 degree Celsius. So, Tongzhen, right, can I write the amount of heat absorbed or released by a substance during a phase change without change in temperature? Tongzhen, if the question is asking about latent heat, then yes, latent here pula. Right? If the question asked about latent heat, then your statement can be used. But if the question says specific latent heat, then I need to see 1 kg of substance. Okay, Tongzhen? Okay, so I'm going to proceed right now with the next page of the textbook, next part of the textbook. This one I sengaja put in one. Okay, now the top part is what we have already discussed just now. I want your attention at the bottom part here because sometimes they ask this kind of question. What does the specific latent heat of fusion of ice is 336,000 joule per kg? What does it mean? Okay, if the question asks what does this value mean, okay, it actually means, okay, specific latent heat formula is given inside page 2. All right, so from 4, please do take note. If you don't know what does it mean, go and open page 2 to find for it. Specific latent heat is Q over M. So the value of 336,000 joule per kg means that it is 336,000 joule of latent heat needed for 1 kg of ice, because this is fusion and it's mentioned about ice over here, for 1 kg of ice to melt and become water at 0 degrees Celsius. The word without change of temperature is being replaced with 0 degrees Celsius. Okay, so that is what it meant by specific latent heat of fusion of ice is 336,000 joule per kg. So I think it is better that you guys write this down. All right, this is very important. Sometimes they ask this question and students go and tembak, don't know what answer come out. Now, specific latent heat of vaporization of water. So which means we are changing from water to gas. All right, is 2.26 times 10 to the power of 6 joule per kg. So this means that there is 2.26 times 10 to the power of 6 joule of latent heat changing from water to gas. So it is absorbed, all right, needed or absorbed for 1 kg of water to boil and become vapor at 100 degrees Celsius. All right, so this is what it meant. Now, what I want you guys to take note over here, all right, this is on the left hand side. Okay, on the left hand side, this is fusion of ice, from ice melting to become water, and on the right hand side is from water to become vapor. Then you look at the latent heat, all right, one for ice, it is 3.36. Let me convert this to scientific notation. 3.36 times 10 to the power of 5 joules of latent heat. But over here, For water to become vapor, it needs to absorb 2.26 times 10 to the power of 6 joule of latent heat. So what does this actually means? Okay, so this actually means that more heat is required. Yeah, more heat is required at, I shouldn't use vaporization. More heat is required to change from liquid to gas. All right, more heat is required to change from liquid to gas. So, which means at that particular moment, they will actually absorb more and release more heat at the interchanging part from liquid to gas and gas to liquid. Because remember one thing, in order for a gas molecule to change from liquid state to gas state, it needs to break away from all its molecular bond. All right, so more heat is being required over there. Okay, so later on, this is the reason why we normally use steaming method to cook things faster. All right. Okay, so let's proceed. Can I go to the next slide already? Are you guys okay so far? Should be okay. So I'm going to change to 3, 2, 1. All right. Now, do write this down. Okay, this is something not in the textbook. Why does the temperature remains constant during a change of phase? During a change of phase, transfer of heat. Okay. Transfer of heat does not cause a change. The transfer of heat does not cause a change in kinetic energy of the molecules. So during melting point at 0 degrees Celsius, the heat is being absorbed, is used to break up the bonds between the solid particles. So the solid particles are freed from their fixed position and are able to vibrate and move among each other. And then when the liquid boils at boiling point, the heat absorbed is used to completely break the bonds between the particles and also to do work against atmospheric pressure when the gas vapors expands into the atmosphere. So that's the reason why, all right, specific latent heat of vaporization is higher compared to specific heat of fusion. Sorry, specific latent heat of fusion, because at vaporization, the when the liquid boils, the heat absorbed is not only to break the bonds between the particles, but it is also to do work against the atmospheric pressure when the gas vapor expands into the atmosphere. So to me, this is a very important point in specific latent heat. Okay, so I'm gonna go next already. Screenshot already. Let's continue.
Yes. Already sent to group chat.
Okay, thank you. All right. So one thing right now, how do we identify in terms of formula first? Okay. So formula for heat, the symbol for heat energy, remember that this Q is also similar to E energy. Energy cannot be created, it cannot be destroyed. So when we are talking about heat energy, we use the symbol Q, but again, it can be interchanged to E, it can be interchanged to work done as well. So when the heat is added or removed at the change of temperature, all right, the temperature changes, okay, the heat is calculated using this formula. Or another words to say, because there's a Q, so that means there's a temperature change. And this formula is when the phase remains the same, which means that the temperature changed, but it's still solid, or it's still liquid, or it's still gas. So we use Q equals to MC theta. And then when do we use Q equals to ML? We use Q equals to ML because you notice that there is no theta symbol inside this formula. So we use this formula when the phase of the object changes. All right, the phase of the object changes, which means from solid to liquid, or liquid to solid, liquid to gas, or gas to liquid. All right, and at constant temperature. So it's either, if it's water, it's either at 0 degrees Celsius or boiling point at 100 degrees Celsius. In the terms of water, then we use Q equals to ml. So this Q equals to ml and Q equals to mc theta, where does the energy comes from? Because if you want to increase the temperature, it needs to absorb the energy, but where does the energy comes from? So in physics situation, the energy comes from electricity. All right, energy comes from electricity, whereby normally in electrical appliances they will give you the power rating. All right, and they will tell us how long do we need to take to heat up that particular the how long does the energy is being supplied. All right, the electrical energy is being supplied, so we take the power rating P multiplied by T. All right, why? Because the basic formula, the general formula for power is energy over time. So electrical energy is power multiplied by time. So this is the power rating from the electrical devices, and this is how long that the electrical energy is being supplied. So you equate this power multiplied by time with either ml or mc theta, depending on the situation. Okay, and do take note, power unit must be in watts, the time unit must be in second. Whenever we deal with physics formula, it must be in its SI unit. Okay, so later on we will deal with some of the questions in order to know how to use this. Okay, where is my mouse? Okay, so one information from the textbook: based on the kinetic theory of matter, the higher the average kinetic energy, the higher the temperature. The latent heat absorbed during melting and boiling does not increase the average kinetic energy of the molecules. Therefore, melting and boiling occurs at a constant temperature. Okay, so one thing that we mentioned just now, okay, mana my mouse pergi? Okay, all right. So here we have to talk about the gas, okay, or not gas. I should say we should talk about the particles, assuming the atoms or the molecules. All right, the particles in physics we normally call it. All right, when the particle moves, it will have velocity. Okay, so when it has velocity, then it will definitely have kinetic energy. All right, when there's velocity, that will have kinetic energy, and this kinetic energy formula is half of mv squared, mass of the particle and then velocity of the particle. All right, so this formula, it's no longer in your KSSM syllabus, but you should know it as well because it's part of your the lower prior knowledge. All right, so in terms of kinetic energy, okay, what happens? Right now we are talking about the whole entire object itself. So we in this chapter we see a lot of average kinetic energy. Okay, so when the average kinetic energy decrease or increase or remains the same. Okay, so when the average kinetic energy decrease, what will happen? The temperature will drop. Okay, and then if the kinetic energy increases, normally the temperature increases, the temperature will rise. All right, and if it's remain the same, the temperature will actually be constant. All right, I think gamma I actually wrote a little bit different from this, but it's still the same, it's interchangeable, and it is actually interrelated, it's still almost similar. If I'm not wrong, I wrote the temperature changes first or something like that in class. All right, but anyhow, the kinetic energy will also look at the temperature. The temperature also affects the kinetic energy of the particles. All right, so when the temperature drops, one more thing that I'm going to add in is that when the temperature drops, normally the energy is being released. All right. When the temperature rises, the energy, heat energy to be more exact, heat energy is being absorbed. All right. But when the temperature is constant, I cannot say whether it is being released or is being absorbed. We have to see the situation, because at some times when at liquid to gas, the energy is still being absorbed, but from gas to liquid, the energy is still being released. All right. So in terms of when the kinetic energy is the same and the temperature is constant, I cannot state that whether energy is being released or energy being absorbed. Okay. So that's one particular part. Right. So five, four, three, two, one. Okay. So here is a table that is actually from the textbook. Okay. It shows what kind of substance at room temperature, which means at 36 degrees Celsius, right? At room temperature, what is the phase? Right? At room temperature, this is solid. Wax is at solid. Lead is actually at solid, copper solid, ice solid, water liquid, petrol liquid, diesel liquid, olive oil liquid, ethanol liquid, oxygen gas, nitrogen gas. Now what you have to see is look at the melting point, at the boiling point. Okay, so wax we have melting point, but so far there is no boiling point. Okay, all right, then the specific latent heat of fusion, which means from solid to liquid, the amount of heat required per kg of wax is 1.45 times 10 to the power of 5 to 2.1 times 10 to the power of 5 joules per kg. Okay, now let's look at, for example, copper. All right, let's look at copper. Copper's melting point is actually 1083 degrees Celsius. So for solid to become liquid, all right, at the temperature of 183 degrees Celsius, we need to absorb 2.07 times 10 to the power of 5 joules of energy for every 1 kg of copper. And then it will boil, become liquid to gas at 2566 degrees Celsius. And at this position, all right, for it to become liquid to gas, it needs to absorb 47.3 times 10 to the power of 5 joules of heat energy, all right, 47.3 times 10 to the power of 5 joules of energy per 1 kg of copper. All right, so you can see that the vaporization, the specific latent heat of vaporization of the amount of heat energy required per kg is actually greater when you want to change from liquid to gas, comparing from solid to liquid. Even if, let's just say, we look at oxygen. Oxygen, all right, from solid oxygen to become liquid oxygen, it only needs 0.14 times 10 to the power of 5 joules of energy per 1 kg of oxygen. And then if it becomes to gas, it needs 2.13 times 10 to the power of 5 joules of energy per kg of oxygen. So in order to change from liquid to gas, we will need more amount of heat energy. All right. So this is what this table is actually talking about. Right, so I'm going to go to the next slide now. All right, still at the textbook. So when ice melt, the ice molecule absorb the latent heat of fusion, causing ice to change from solid to liquid. So changing from solid to liquid, you absorb latent heat of fusion. When the water boils, all right, the water molecule absorb the latent heat, causing it to change from liquid to gas. So when the water vapor condenses, the water vapor molecules will release heat energy. All right, it will release the heat energy when it changes from gas to liquid. So that's the reason why I put this down here. Absorption of latent heat during melting and evaporation can be used to give the effect of cooling. All right. The absorption of latent heat during melting and evaporation can be used to give the effect of cooling. So latent heat releases during the condensation, however, is used for the purpose of heating up. So when they are being released, right? When it's being released, it's used to heat up purposes. Okay? But when the latent heat is being absorbed, okay, we use that as a cooling effect. All right? So specific latent heat, I want to check something for a while before I talk about this. Mana itu table? Okay, now I understand. No wonder I talk. I've forgotten about one particular table. Okay, I'm gonna finish talking about this first. Then I'm gonna go back into the 2 pages on the textbook that I've forgotten to put into my PowerPoint slide. Now, specific latent heat of vaporization is required to change the phase from liquid to gas. So this heat is absorbed from the surrounding. So when it's being absorbed, the surrounding will actually be cooler. So when a liquid evaporates, the liquid molecule will absorb the heat to break the bonds between the molecules. The surrounding loses heat, therefore evaporation causes the cooling to the surrounding. So for the form 4s who's having the textbook, can you please highlight this sentence, and for the form 5, please write down this sentence. All right, because this is how we steam food. And this is also the same reason why, like for example, when we sweat out, we feel that it's much more cooling. All right, because when the liquid evaporates, all right, when we start to sweat and our sweat actually evaporates to become gas, the sweat actually absorb all the heat around us, all right, including the heat from our body. So the heat that is being absorbed breaks the bond between the molecules. So when the water absorbs the heat from our body or from the surrounding, all right, the surrounding environment, the surrounding and our body temperature will actually loses the heat. So our temperature will drop, causing us to have a cooling effect. All right, so please underline and please identify this. They might come out in terms of a 4 marks application question or a 2 marks question in paper 2. All right, so let's just say application of specific latent heat. The melting part is where cooling drinks and food with ice cubes. It is the ice cube that will absorb the heat to melt from solid to liquid. But because when it absorbs the heat, the surrounding drinks and the surrounding food will actually decrease its temperature. Okay? Evaporation is whereby liquid evaporates to become gas. All right? So the liquid will absorb the heat, so the body will actually have a cooling effect during hot day or when we sweat. And it's also the same system inside the cooling system of the refrigerator, and it is also the same cooling system of the air conditioner. All right, our air cons. During boiling time, all right, boiling, it is cooling as the liquid nitrogen boils. All right, and then for condensation, condensation is very important in terms of steaming the food and heating the espresso coffee. Okay, so I think the next slide is all the calculation part already. All right, so I'm gonna jump back to the textbook for a while. I skipped this part because I didn't copy. Okay, now, okay, let me quickly drink water first. Okay, before I start, Gamma, please keep quiet first. All right, if you look at this, don't respond anything yet. If you look at this temperature versus time graph, all right, we see that this is actually the heating curve. All right, this is actually the heating curve for a substance. Can I ask, what substance do you think that this curve belongs to? Could it belong to ice and liquid, or could it belong to something else? That's why gamma cannot respond. So from 5, for omega, and for alpha, where do you think this heating curve belongs to, what substance? Looking at the graph, it should give you a hint. So I should make the question more easy. Could this heating curve belong to ice, water, and vapor? Yes or no? Chongwei, where were you? All? Yes, it belongs to water, Daniel say. Yes, it belongs to ice, water, and also vapor. Anyone else? Ian say ice. Chongwei said opposite of Daniel's answer. Form 5, I know you're in here. Does this belongs to ice, water, and vapor? Chongwei said opposite Daniel. Imran said opposite Chongwei. Opposite of Imran. It's always more interesting to kind of teach extra class with the form 4s though. At least form 4 give me all funny stuff to let me relax down a bit. Alright, so for information, no, this does not belong to ice, liquid, ice, water, or vapor. I have no idea if this is phenolphthalein. Alright, why? Okay, why does this not belong to ice, water, and also vapor? Because 0 degrees Celsius is down here. Alright, so ice is supposed to melt at 0 degrees Celsius, which means the heating curve does, if this belongs to really belongs to what then the x-axis supposed to be at here, Alright, but the x-axis is still at the bottom part with the 0 degrees Celsius down here. So this does not belong to ice, water, and also gas. Okay? Now, all right, so you have to understand how to explain this heating curve, even though that this heating curve, you looked at it for quite some times. But we're going to talk about the kinetic theory of gases, all right, the kinetic theory of molecules. This term, kinetic theory of molecules, or the kinetic theory of gas, is very important because it tells you what happens when the temperature change. All right, so let's start right now. Let's start with this part. Okay, let's start with this part whereby whenever whenever it is diagonal, it is actually one phase only, one phase of matter. When it's horizontal, there's two phase, either solid, liquid, gas, all right, that exists at this horizontal line. So whether the diagonal line is going up or the diagonal line is going down, it only belongs to one phase of matter. Okay, so let's start with here. All right, so from P to Q, this is actually a solid matter. Solid, when the temperature continue to rise, this is whereby the temperature continue to rise. This x-axis is time, so we don't bother about the x-axis for now. When solid continue to rise in terms of its temperature, it means that the heat is being absorbed. Always remember, when heat is being absorbed, the temperature will increase. Okay, when heat is being absorbed, the temperature will increase. When the temperature increases, the kinetic energy of the molecule increases. If you were to recall what I wrote previously here, all right, When the temperature increases, the kinetic energy increases, the heat energy is being absorbed. All right. So this is what happens from P to Q. But at point Q, all right, point Q is whereby the melting point happens. All right, so point Q, solid starts to melt. All right, the solid will start to melt. And then at the horizontal line of Q to R, the solid is melting. When solid is melting, this means that solid and liquid exist at the same situation. All right. Solid and liquid exist at the same situation. All right. When solid and liquid is existing at the same situation, latent heat is being absorbed. All right. Because this is changing phase, the temperature doesn't change. It's at the melting point. So latent heat is being absorbed to weaken the bonds of the molecules. So whenever I highlight something, please make sure you underline or highlight in the textbook lah, huh? So you help the juniors to highlight the textbook already lah, huh? Okay, or you underline or you write wherever you can. Now, what happens here? All right, when the heat is being absorbed, the temperature is constant. What happens in terms of the kinetic theory of molecules? The molecules are released from their fixed position and they move throughout the liquid. Okay, this is what happened at the same state, the same temperature. The kinetic energy does not increase and the temperature remains constant. This is what happened at the solid line. Latent heat is being absorbed. It is absorbed to weaken the bond between the molecules, not to break away. All right, please take note. Solid to liquid, it's to weaken the bond. All right, the molecules are released from their fixed position and they are allowed to move throughout the liquid. The average kinetic energy does not change, all right, does not increase, and the temperature remains constant. But at point R, that is when all the solid has already melted to become liquid, fully liquid at point R, at this position. So after that, heat is continued being absorbed. So when heat is continued being absorbed, the temperature will increase. Kinetic energy of the molecule increases. So I'm going to write one more thing here. This heat that is being absorbed is Q equals to mc theta. All right, this heat energy that is being absorbed is Q equals to mc theta. So that is actually specific heat. Okay, because the temperature changes, all right, the substance doesn't change, it's still liquid form, the temperature changes. So this part, this curve is where we use Q equals to mc theta. Okay, so at point S, all right, at point S, what happens is the liquid will start to boil. All right, when the liquid starts to boil, all right, heat energy is continued being absorbed. So from S to T, that is when liquid is boiling. When liquid is boiling, it means that liquid and gas exist at the same time. All right, liquid and gas exist at the same time. So at point T is when all the water have finished boiling. All right, so if you recall back in your the simulation that I had just now, all right, this simulation that I had just now for those who just came in, okay, so at this position, where is it? Okay, at here, all right, liquid starts to boil. Okay, the liquid starts to boil, the temperature continues. So when you're actually cooking your Maggi or you're heating up the water so that it's actually much more the water filter water is not temperature not high enough, then you go and use the stove and boil it, right? That is still considered as 100 degrees Celsius, all right, but we cannot consider it as fully vapor, because normally when we consider at this position, all right, at point T is where all the liquid has been boiled. All right, when all the liquid has been boiled, it is actually at this position whereby all the liquid here has already changed to become gas, and normally this is not what our mothers or our parents want to see lah. Okay, because when this happened, that's when the pot starts to get black and then the smoke comes out from the stove already lah. Okay, so Wait, what happened to my Google Meet? Okay, hilang again. Okay, so over here, what has happened? All right, when the constant temperature, the latent heat is being absorbed. All right, latent heat is being absorbed. Now it is absorbed to break the bonds between the molecules. So the molecules separated far from each other, and the kinetic energy does not increase here again. When the kinetic energy doesn't increase, the temperature will remain constant at 100 degrees Celsius for boiling point. Okay, so the key word here is number one. This is actually specific latent heat of fusion. All right, this latent heat is the specific heat of fusion. This specific heat capacity would be for vaporization. All right, so this is used to, the latent heat that is being absorbed is to break the bond. But for melting point and also for freezing point, all right, for melting point especially, it's to weaken the bond between the molecules. So this is the key word that you have to identify and you have to remember. Okay, so this is for the heating curve. Now let's look at the cooling curve. Testing again. Does this belong to ice, water, and also gas? No. Why no? Why no? Why is it no? Correct. All right. Darren's answer is correct because it doesn't freezes at 0 degrees Celsius. Okay. All right. So right now we have a cooling curve. All right. Cooling curve of an object. Last time I learned it as what Nathaniel actually said just now. It's actually the naphthalene, right? But then in physics, we don't only talk about a specific chemical, we talk about all the chemicals. So that's why we don't mention a specific uh, chemicals or the specific substance, all right? We just consider it as an object instead. Okay, so in terms of cooling curve, so the beginning part is going to be gas. So the temperature drops. When the temperature drops, it means that the kinetic energy decreases, heat is being released. All right. So here, the heat that is being released because of the temperature decreases, the temperature change, we use again Q equals to mc theta. All right. So remember, this indication of theta means that when there is a change in temperature. Okay. So when the temperature drops, all right, kinetic energy decreases, the heat is being released. But when it reached point Q, all right, when it reached point Q, this is when something else happened. Gas start to condense. At Q to R, gas is condensing, which means it exists in terms of gas and liquid. All right, it exists in gas and liquid state. So at gas and liquid state, the heat energy is being released and molecular bonds are being formed. So these are the key words that need to be seen. All right. The molecules will move throughout the liquid, but the kinetic energy of the molecule does not decrease. Can you please add one word? Average kinetic energy does not decrease. All right. When the average kinetic energy does not decrease, the temperature is constant. All right. So at point R, all the gas has already fully condensed, which means it is now in liquid state at point R. Okay. Then from R to Q, the heat is continued being released. So if the heat is being released in this case, right, when the heat is being released, the surrounding will actually be heated up. Okay, because the heat is being released, so the surrounding environment will actually be hot. Then the temperature decreases. Okay, kinetic energy of the molecule will continue on to decrease until point S. At point S, that is when liquids start to freeze. And then from S to T, the liquid is freezing, means that it exists in liquid and solid state. All right, exists in liquid and solid state at point T. That is when all the liquid has completely frozen. Now, what happens? This part is actually where all the kinetic theory of the kinetic theory of the molecule comes in. All right, what happens when the heat is continue being released but the temperature doesn't change is because the latent heat released so that the bonds between the molecule is strengthened. So from gas to liquid, the bonds are formed, but from liquid to solid, the bonds are being strengthened. The molecule vibrates around its fixed position, but the kinetic energy of the molecule does not decrease. And because it doesn't decrease, it is constant temperature. All right, so you can see all the words that I've highlighted there. This one is a 4 marks question already, lor. Okay, so from 4 and from 5, please do take note. All right, so at T to U, that's when the solid starts to cool, heat is being released, all right, temperature decreases and kinetic energy of the molecule will continue on to decrease. All right, so this is the cooling curve. Okay, so normally when they ask in terms of the kinetic theory of gases, this is the part lor. This part, when the heat is being absorbed or the heat is being released. Okay, so we're gonna take a quick 5 minutes break over here for me to go and get something to cool off my throat first. We'll come back in about 5 minutes time. So right now it's 9:04. We'll come back at 9:10. Okay. Okay, hope you're back. There's this application that I'm have showing right now in the PowerPoint slide, but it's not inside textbook. All right. So if you want this PowerPoint slide, please screenshot. All right. Or I'm gonna start scribbling around this already, because I think these are the questions that they will normally ask in the exam. Okay. But somehow they only put two things inside the textbook, which is uh the refrigerator, and also they have a steamer question over there. So we'll discuss the steamer questions, but I'm going to talk about the applications of specific latent heat first. Okay, because anyhow, in SPM wise, even the Form 5 would notice in the trial wise, it's 60% conceptual question. Then there's only remaining about 40% of calculation question. So the calculation question normally is all the simple basic ones I noticed for the trial SPM this round. So I think for Form 4 should be almost similar, I guess. I'm not very quite sure. Okay, now let's talk about the application of a specific heat, latent heat. All right, specific latent heat. So over here, all right, number one, the drinks can be cooled by adding in several cubes of ice. So what happens here is that normally when we have water, we have drinks, all right, the drinks temperature, let's just say at 80 degrees Celsius. All right, and we consider that to be hot. If you want to drink Milo ice or day ice or anything lah, okay. Normally the water existing itself is actually at a higher temperature. So what happens here is that they will put in ice cubes inside there. All right. So where does the specific latent heat appears? All right. When the ice actually melts from ice to become water, they actually absorb heat. Okay, so they actually absorb heat. So where did they absorb the heat from? So we know that heat is a type of energy. Energy cannot be released, it cannot be created, cannot be destroyed. So when the ice want to melt to become water, it obviously need to absorb heat. So where does the heat comes from? The heat comes from the drinks. All right, whereby you want to change the temperature of 80 degrees Celsius of the drinks to lower it down to probably 10 degrees Celsius. So when there's a temperature change here, all right, it will actually release out the heat because it's decreasing the temperature. So the drink will release the heat and the ice will absorb the heat. I repeat, the drink will release the heat. Let me write this. All right. The drink will release the heat and then the ice will absorb the heat. All right, so this is when ice melts, a large amount of heat is being absorbed, and this lower the temperature of the drink. Why? Because the drink temperature will decrease, the ice will melt, become water, and then the temperature will increase after that. All right, so this is how specific latent heat is being used in cooling the drinks. Second part is actually this question. This question I think came out in 2020. 2020 or 2021, I don't remember. I remember there's a question regarding the ice box. All right, freshness of the fish and the meat can be maintained by placing them in contact with the ice. Why? Because when the fish and the meat, right, it has a higher temperature, ma. So when they are placed in contact with the ice with large latent heat, right, ice can absorb a lot of quantity of heat from the fish as the ice melt. Right? So the heat energy from the meat or the fish is being released and is being absorbed by the ice. So that's why the food can be kept at low temperature for an extended period of time. Okay, so that is again, the ice actually absorbs the latent heat to change from ice to water, but the heat that is being absorbed is released out from the fish itself. All right, the temperature of the fish is normally at higher. Now, what happens in steaming? Okay, this is one of my pointer. Okay, now when we steam food, okay, when we steam food, water has large specific latent heat of vaporization. All right, vaporization means from water to gas, or from gas to water, vapor to water. So this property enables the steam to be used for cooking by the method of steaming. So when we steam, all right, water change become vapor, but it is the steam that helps us to cook the fish or the food. Why? Because when the steam condense, when the gas, all right, when the gas or the vapor, all right, the vapor change back to liquid, condense back to liquid, it will release heat energy. All right, and we remember, if you remember just now when I mentioned regarding heat energy, sorry, the specific latent heat of vaporization, its latent heat is higher compared to the latent heat at fusion. All right, so when vapor condenses to become liquid, the latent heat that is being released is very, very high. All right, so that is actually how enables the food to be cooked faster at a faster rate. Okay, so which means that, okay, the steam condenses uh to become vapor, sorry, the steam condenses to become liquid, it releases heat energy, and the latent heat is directly released to the food and enables the food to be cooked at a faster rate. Okay, so that is actually for steaming food. Then next part is actually this one I think some of us would experience if you were to go into the kitchen now. Okay, word of advice, please do, Rajin go to the kitchen after this, especially for the form fours. Okay, how to cut the veggie, how to actually cook or use the pot and everything, it's all related either to physics or biology already for Amali. So we have to be very careful when we open the lid of the pot when the water is boiling, because honestly, if you would notice one thing, it's not the if you get if some drops of boiling water hits your hand, it's not as painful as the steam actually hits your hand, you know. When you actually open a pot, the lid of a pot, when the pot it has boiling water on it, the steam, when actually it condenses on your hand, the energy, the heat energy that is being released by the steam when it condenses on your hand is higher than one single drop of water hits your hand, you know. The one single drop of boiling water hits on your hand, the heat energy is actually much more lower compared to the heat energy that is being released by the steam when it condenses back to liquid. That's why it's much more hotter when the steam touches our hand. All right, because water has large specific latent heat of vaporization. So when the steam condenses on the skin, a large amount of latent heat is being released, which can actually cause serious burn. All right, so the burn is much more stronger due to the steam compared to the boiling water, honestly to say. All right, because the amount of heat energy that is being released, the latent heat that is being released by the steam is actually very high. All right, if the water touches you, the most that it does is it changes temperature. That is actually heat capacity. Heat capacity value is always lower than latent heat. All right, latent heat is normally higher compared to heat capacity. Okay, so this one you have to be aware of. All right, so this is actually some of the applications of the specific heat capacity. Hey, mana my pointer go? Okay, so I'm gonna go next. I'm gonna ignore this one first. This is actually inside the textbook. Ignore the class point first. All right, I already mentioned how the fish is being heated by the explanation just now. All right, so I guess you guys have already copied that down. All right, so this is an example inside the textbook. All right, figure 4.22 shows a 480 watt immersion heater, all right, used to melt ice. If you remember just now what I said, when we want to change the phase, the state of matter, all right, to change from solid to liquid, liquid to gas, or anything, all right, when we want it to change and increase the temperature, we must release, we must provide the heat energy, or we must provide the energy. So in terms over here, this is where we use electrical energy. All right, we use electrical energy to convert it to heat energy. Okay, so over here you see they will always give you the power rating. This is the power of the immersion heater used to melt the ice. So when it melts the ice, which means we will have to see from ice going to water at 0 degrees Celsius. Okay, so in 120 seconds, this is actually the time. The reading of the electronic balance decreased by 0.172 kg. So this is actually the mass. Now, I'm showing you this, all right, in terms of a few things because it shows you the assumption. And sometimes the question actually asks, what assumptions do we make? So this is very important when we're dealing with heat energy. Okay, so what is the mass of the ice that has melted during the heating period? So when it heated period over here, the temperature, the electron balance actually decreased by 0.172 kg. So we know that the mass that has already melted is obviously 0.172 kg. But there's a few assumptions, and that's the reason why I took this example out from the textbook to explain right now. The first assumption that they made, all right, is that the ice is melted by heat. Okay, ice is melted by heat from the immersion heater only. Okay, this is one assumption that it made, whereby, all right, the ice at room temperature, and normally we carry out this experiment would be during daytime. The assumption that this experiment is that all the heat that is being supplied by the immersion heater is fully used to melt. All the ice will absorb the heat by the immersion heater only, and not by the surrounding environment or the experimental's hand. Because now sometimes you will hold the beaker, right? The minute you hold the beaker, you're transferring energy inside. So in terms of ideal cases, normally we have to make a few assumptions. All right? Because as I said, whenever we learn something, we learn it as ideal case. But when we carry out experiment, we know that it's not ideal case, it's realistic situation. All right? So if we are carrying out this experiment or activity, the ice is melted by the heat that is coming out from the immersion heater only. Okay, so the amount of heat that is being absorbed by the ice comes from the heat that is being released from the immersion heater. Okay, and then another thing is all water from the melting ice will flow out from the container. Okay, all right, all water from the melting ice flows out from the container. So it means that there's no water that actually remains inside there. So when the electronic balance decreases its mass by 0.172 kg, it is only full with ice inside there because the water actually gets flowed out. All right, so the mass of the ice melted decrease in reading of the electronic balance. So therefore, the mass of the ice that has melted is 0.172 kg. Okay, next, calculate the specific latent heat of fusion. Again, they made an assumption that I want to emphasize here. All the heat supplied by the immersion heater is fully absorbed by the melting ice. All right, all the heat supplied by the immersion heater is fully absorbed by the melting ice, because there are sometimes they will ask assumptions. So these are the assumptions that you have to be aware of. Look at the question, look at the diagram. What are the assumptions that need to be made? Okay, then the second assumption is no transfer of heat from the surrounding into the apparatus, which means that we assume that this activity, when it's being carried out, the surrounding environment, the heat from the human beings around surrounding all this equipments doesn't transfer heat to the apparatus itself. All right. So the sentence that should come out in exam should be this kind of sentences. Okay, so no transfer of heat. These are the assumptions that I want you guys to be alert of. Okay, Form 4 and Form 5 alike. All right, so I hope that these are the assumptions that we make during heat energy. All right, so I'm going to go next. I'm going to show you guys right now how to do calculation questions. They don't give too difficult questions for calculation, um, but please don't be afraid, all right, when they change the type of question, because the example that I have right now is quite straightforward. But when in exam, the question might comes out in situation, contextual questions. Contextual means that they might say that I have an ice box and I'm putting ice inside there. Okay, so you have to be clear of the situation. Wait, you have to be clear of the situation and just answer accordingly. Can you give me a moment right now? Sorry. Okay. Sorry about that. Okay. So right now the question says the specific latent heat. Okay, let me give you guys and teach you guys a few tips. When to use Q equals to MC theta, when to use Q equals to ML. You see this word, specific latent heat? Specific latent heat starts with the letter L. So when you want to calculate this heat to melt, so we use Q equals to ML. Later on, I will teach you guys when to use MC theta. I have another question that combines these two. Okay, so the specific latent heat of fusion of ice is 336,000 joule per kg. What is the quantity of heat required to melt 2.5 kg of ice at 0 degrees Celsius? So what does this mean? Normally, I would do one thing in this question. Number one, learn how to write out all the informations carefully. Number two, in an exam, when you write your answer, please don't write too big your handwriting, okay? Or else it will look seriously messy, hinting to Form 5. So over here, specific latent heat is 336,000 joule per kg. The amount of quantity of heat required, Q required, to melt 2.5 kg of ice at 0 degrees Celsius. So this is hinting you already that you're supposed to use Q equals to ML. The word specific latent heat with the L symbol there, that is latent heat. So it already tells us we need to use Q equals to ML. So over here, Q equals to ML. The mass is 2.5. Latent heat, this is kg, joule per kg. So all is in SI unit. So 336,000. All right. So oh no, my calculator's at the back. So when you press the calculator, please cross check. I know the answer is up there. Okay, when you write your answer 840, cross check the answer, press the calculator again, because I know sometimes this answer can be wrong. You can leave the answer like this, but I would prefer to see the answer as 8.4 times 10 to the power of 5 joules. I prefer to see the answer like this. Okay? Why? Because if you write any terlebih 10 or terkurang 10, it doesn't not so obvious, you know. When you write it as 8.5 times 10 to the power of 5 joules, the answer is more accurate. Okay? So this is actually a very simple, straightforward type of question. Tongzhen, yes, can. You can also write it as 840 kilojoules. Can, no problem. If the question doesn't state that you have to write in scientific notation, no problem to write that answer. But make sure you have this first before you write this. Okay? So the next part is, let's go to the next question. What is the quantity of heat required to convert 4 gram of ice to steam at 100 degrees Celsius? So please do take note over here. Okay, so I am going to draw out a phase change. All right. 4 grams of ice will obviously at 0 degrees Celsius. Okay, ice at 0 degrees Celsius will have to change to water at 0 degrees Celsius. Okay, then after that, the water, because it has to change to steam at 100 degrees Celsius, so the heat will continue be provided until it becomes water at 100 degrees Celsius. Okay, when it's at water at 100 degrees Celsius, then only it will change to become steam at 100 degrees Celsius. So draw this first. Okay, so what happens here is the amount of heat required. When ice becomes water at constant temperature, we use Q equals to ml. This is latent heat of fusion. All right. Then from water 0 degrees Celsius to water at 100 degrees Celsius, it changes temperature from 0 degrees Celsius to 100 degrees Celsius. We use Q equals to mc theta. Okay. And then from water to steam at 100 degrees Celsius, we use Q equals to ml back again. And this is latent heat of vaporization. That's the reason why the question will give you latent heat of fusion, latent heat of vaporization, and latent heat of heat capacity of water. So the amount of heat that is required to convert 4 grams. So right now I have to change my gram to kg. So that would be 4 times 10 to the power of negative 3 kg. Okay, it's same as 4 divided by 1000. So I just write it as times 10 to the power of negative 3. So the amount of heat that is required, so which means the total heat required, Q, total heat required would be the heat of latent heat of fusion plus heat capacity, this one, plus latent heat of vaporization. So here, we assume one thing. There's one assumption I'm making right now. 4 grams of ice fully melted become 4 grams of water. And 4 grams of water will fully become 4 grams of steam. All right, that is my assumption. Okay, so here, this is ml, this one is fusion, plus mc, change of temperature, plus this is vaporization, vapor. Okay, so that would be, I'm gonna take out my m, I'm taking it out already. I'm gonna write one more space. I know when I skip steps, someone's gonna get confused. Latent heat of fusion plus specific heat capacity and change of temperature plus latent heat of vaporization. So my mass is 4 times 10 to the power of negative 3. My latent heat of fusion, 336,000 plus heat capacity of water, 4.2 times 10 to the power of 3. Please be careful when you press your calculator. Change of temperature, 0 to 100 degrees Celsius. So the change of temperature is 100 degrees Celsius. Plus latent heat of vaporization, 2.26 times 10 to the power of 6. So you will notice one thing, I'm very sensitive with my brackets. So can you all please press your calculator because I don't have my calculator with me right now. Press your calculator, see whether you get the same answer or not. Press your calculator very, very carefully and see if you can get the answer. Brian get 12064, the same. Darren also got the same. I would say Brian and Darren both salah. Rabika got 1.08 times 10 to the power 4 joules. Rabika answer, your answer is quite far away from the answer schema. Brian, the reason why you're wrong is because there's no unit. Rabika, check back on your brackets. Please, 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 please remember the unit. Zhongwei, I insert the unit for you is equivalent to 0. And Zhongwei, your answer terlalu jauh salah. Last year SPM 2021, your seniors didn't write unit directly 0, you know. Syntax error, calculate again. When you do calculation in your calculator, that's why if can, don't skip steps. Alright, simplify this part first. Simplify here, add the values, then only multiply. Don't be so greedy in calculating everything into your calculator. That is when you get all these errors. So since Brian and also Darren got the same answer minus the unit, so I consider that the answer is correct lah, okay? Try to recalculate it back again. The answer should be 12064 joules. Got it? Rebecca, did you manage to get back the correct answer? Jarash got it. Good.
Sorry, what was the answer again?
Here, up here.
Oh yeah, I got it.
12064. Okay, good. Alright, so I'm going to proceed right now since most of you already got it. Okay, now, wait right now I want you guys to enter the class point because this is a question that I want to let you guys try to discuss first. So please kindly enter the class point. Okay. You would know by now it is better to enter class point using your handphone. You can actually enter that using your laptop. Still can, no problem. It's just that there will be some answers very difficult. When I ask for screenshot of your answer, then I will see a lot of mouse written answer already. Every single time I see Chirong's short name. Rebecca, you can remain using your laptop. It's just using your handphone to actually answer only, that's all. Alright, so for the rest of you, the class point code is still up here. Alright, so I'm going to show the question out already. Okay, so I'm going to show you the question first. You can still try to enter class point. Alright, this is my question over here. So while the rest of them are still trying to look at the getting into class point. So saja, I would just want to erase off all the BM wordings. Alright, so diagram shows different methods of cooling coffee of equal mass. The coffee has the same mass. So coffee in cup A is cooled by putting the ice cubes inside the cup. Coffee at cup B is cooled by putting the ice cube outside the cup. Okay, so initial temperature of each cup is 0.5 kg of coffee is 75.5 degrees Celsius. All right, so that is the initial mass and also the temperature. All right, so I'm going to close the class points here first. So I'm asking for the answers. Number one, the melting point of ice involves the absorption of latent heat of fusion. What is meant by specific latent heat of fusion? So this one doesn't need that question yet, so I'm not putting it out first. All right, so obviously you can refer to your notes or your textbook on the definition. So this is a short answer, so key in your answer inside. Do take note, this is not a general question. It's not specific latent heat, but it's specific latent heat of fusion. When the question mentions specific latent heat of fusion, fusion means it's either from, you see, the melting of ice involve absorption of latent heat of fusion. So which means it's specifically from ice to liquid. All right. Please be very careful. Don't just look at the second sentence, what is meant by specific latent heat of fusion. Here, melting of ice involves the absorption of latent heat of fusion. There are 4 people responded. There's 26 people inside my class point. So the time now is 2 minutes plus. So I'm waiting for a few more to give the answers. All right, I'll close the submission at 3 minutes mark. Right, 30 seconds to go. Now, I'm directly teaching you guys how to answer the questions, a refresher for the Form 5s, so the Form 4s. All right, always remember that if the first question is asking about specific latent heat of fusion, the rest of the question will be related to specific latent heat also, or the rest of the question will be related back to the heat chapter. So the first question will tell you what chapter does this question comes out from, or what subtopic does the question comes out from. All right, so that's the 3 minutes marks. I'm closing the submission. And I have inserted all the answers as for review cases. All right, so over here, now, the question asks, ignoring this, the question asks, all right, what is meant by specific latent heat of fusion? Okay, so I'm telling you the answer for my situation. This is melting of ice. It's already indicating that ice is going to become water by the absorption of the latent heat of fusion. Okay, so what is meant by specific latent heat of fusion? So it would be the energy absorbed for, because it's specific, so for 1 kg of ice to change phase to water at 0 degrees Celsius. If you don't write 0 degrees Celsius, but you mention at constant temperature, still acceptable. Why do I write specific ice to water? Because it's already written fusion over here. All right, and the top sentence tells you it's the melting of ice. So from 4 and from 5, please do note when you see something like this, look back at the top part of the question. All right, how does it wants you to write? Whenever you see the word specific, make sure there's a 1 kg inside your answer. So let's look into your answers right now. Okay, so amount of energy required to change state of 1 kg without changing the temperature. Now, for Imran, in this case, if I'm going to be strict, I will give you a wrong. If I'm being kind-hearted, I'll give you a correct. All right, but because the question says for fusion of vapor already, fusion, so you have to state specifically. Okay, so PZ is who? Amount of heat required to change 1 kg of substance from solid to liquid, good, without changing the temperature. Okay, this one's still acceptable because I see the word solid to liquid. Okay, amount of heat that is absorbed during melting, this one tak payah. During freezing, here tak payah because it's on top. Rabika, on top already mentioned ice melting already. So 1 kg of substance without any change of temperature, this one I can accept. The amount of heat absorbed during melting of 1 kg of substance without any change of temperature, okay. Quantity of a heat that's absorbed during melting, again, Chi and Rap's answer, hampir sama lah ha. Okay, quantity of heat required to convert the unit of mass. This one, no. To not convert, to change 1 kg of mass of substance from liquid to solid to liquid state without changing the temperature. Okay? Lionel, amount of heat energy needed, okay, to change 1 kg of substance from solid to liquid without changing temperature, okay. Amount of heat absorbed during melting to change 1 kg of solid to liquid. Brian, sorry, I don't see without change of temperature. It's a key word that needs to be there. Okay. Specific heat absorbed during melting. Again, Harshini is the same answer as Rabika and also Chirong's without any change of temperature. Alif, heat absorbed during melting of ice. Alif, sorry, ini dah salah. I need to see change of 1 kg from solid to liquid without change of temperature. Erica, substance that is absorbed. The substance is being absorbed. Erica. Alright, energy that is being absorbed during the melting of 1 kg of substance without any change in temperature. Because I see the melting word, I still can accept. Okay, quantity of heat that is being absorbed during melting of 1 kg of substance without, this one also still can accept. No one used 0 degrees Celsius. Without any change of temperature, solid liquid constant temperature, heat release. Okay, so most of you guys are giving me the almost the same answer. Absorbed during melting, okay. Okay, so most of it is almost there. Alright, okay. Next. Showing you the question. Okay, I'm showing you back the original question. Is it okay if we put substance instead of ice? I will still accept lah. Alright, normally we will still accept lah. Okay. Now, if both cup of ice reach the final temperature at 25 degrees Celsius at the same time, which cup of coffee requires more ice? Alright, which cup of coffee will require more ice, and explain your answer. So this is the original question. Cup A is cooled by putting ice cube inside the cup. Cup B has ice cube outside the cup. So you have to answer two parts right now. 1 marks for each. Which cup will reach the final temperature if it reached the final temperature at 25 degrees Celsius? Which cup will require more ice? A or B require more ice? Why? I have answers coming in already. Which cup will require more ice and why? So I have four answers coming in. I'll wait for the 5 minute timer there. Seven people responding. Time right now is 3:40. Ray, I see your answer very long. In exam, the question will be just like this, one single line for 1 mark one. They'll give two line if it's a definition. So which means the answer that I want is actually very short. Okay, normally in exam the answer that we want is very short one. So no need too long. I still have 30 seconds to go. If your handwriting is very small, then you will see me writing over there. Can you write bigger? And please do one thing, all right, Form 4s and Form 5, a reminder again over here. Number one, please practice yourself not to use gel pen or ink pen. Okay? Try not to use gel pen and ink pen, especially for the Form 5. In SPM, they will scan your answer. So if you use gel pen and you use ink pen, sometimes the writing cannot be seen clearly one. Okay, I'm gonna stop here to show you guys the answer. I'm inserting all the answers in right now. Okay, so alright, so the short answers right now. Question is which one will actually require more ice? So I think most of you are answering it correctly. The answer is yes, B. Okay. Um Here, explain your answer. This is only a 1 mark question. Okay, so over here, let's see what answers did you guys actually responded. Here Rabika actually says, where's my okay. Rabika says because in cup A coffee is directly in contact while cup B is ice in outside the cup. Okay. Now, thank you for being an example, Rabika. Okay, when the question asked us, okay, which cup requires more ice, and then the question asks you to explain your answer. So your answer is cup B. So you have to explain your answer. When you explain your answer, don't explain cup A. Jangan jawab, jangan jelaskan cup A. Just explain about B enough. Okay? Don't waste your ink. So over here, cup B is correct. So I know everyone answer cup B lah, okay? Reason, all this tak payah. Cup B, the ice is outside the cup. Not very accurate answer. Okay? But Li Xing's answer is correct. Ice couldn't absorb the heat from the liquid directly. So this is a more accurate answer. Okay? Lucas, because latent heat is not directly absorbed with the placement of ice in cup B. Okay, this one I can accept, but very high level answer, Lucas. Xin Yan says ice cubes are placed outside of cup B. Ice cube will absorb heat energy from the surrounding. What I will do is I will bracket this and I will just thunder here only, and then I won't read anything else already. Okay? So Chongwei says B, because it's outside and not in the substance, ice molecules cannot absorb latent, making it slower. Latent apa? Alright. But then I will say because it's put outside and not in the substance, Chongwei, your answer will have a question mark. You see, you have to write everything in the question. Alright. In SPM, you got no option to explain your answer. Hinting from 5 again. Cup B, transfer of heat between substance and ice will cause the ice inside to... Huh? No, sorry, Imran. Alright. Just direct answer that the ice outside absorbed the temperature around it. Okay? Alright. Seriously, who's Tizak? Tarani, is it? Cup for Brian's answer, cup B requires more ice because ice will help cup B to cool down the coffee when it melts due to its large. Salah. Sorry, Brian. Long answer, but Dongzhen. Okay, sorry, yeah. Okay. So Brian, too long, but the answer's not there. Darren, you don't have to write require more ice directly. Cup B is sufficient. Again, Darren, don't answer cup A. I will go look at ice in cup B is absorbing heat from the surrounding. Yes, this is the answer that I'm searching for. Alright. The ice in cup B is absorbing heat from the surrounding or absorbing heat from the temperature around it. Okay, here, Audrey, ice outside the cup can be affected by the surrounding. Okay, correct. Ray, sangat panjang. Ray, same situation. Where is your answer for number 2? I see B number 1. Ray, mana answer for number 2? Okay, and then Chirong, please don't explain about cup A in exam. I will cancel all this and then I will write one sentence saying you're wasting your ink. So for cup B, ice is blocked by the cup's outer surface. The surface acts as an insulator. It's not the insulator which blocks the thermal contact. Okay, you don't need to talk about the thermal contact because in specific latent heat, we don't talk about the heat thermal contact. Okay, so unfortunately, salah. Okay, sorry, Mr. Chichi. Yang B, ice is put in the cup, coffee will be released. You see, Yang, you're explaining if ice is put in the cup. This is what happens when oxygen has 2 electrons. I have no idea. I don't understand already, Rabika.
It's an inside joke, sure. Don't worry about it.
Okay. So, Shuyang jawaban salah. Okay. Lionel cup B because the ice outside the cup is influenced by the surrounding temperature. Again, don't talk about A. So influenced by surrounding temperature, I can accept that. Li Xuan, cause the heat released by the coffee does not absorb. Alright, good. This also I can accept. Erica, because more ice is needed to absorb the heat from the surrounding to reduce the temperature of the liquid. Erica, do you understand what you wrote? More ice is needed to absorb the heat from the surrounding to reduce the temperature of the liquid. So I can say wrong. Sorry. If I'm being kind-hearted, I would say more ice is needed to absorb from the heat. Memang salah lah. Sorry lah, Erika. Okay, now next part. Okay, let's finish up this question. I'm gonna show you guys the question back again. You all understand the question just now, So the explanation is cup B because the ice absorbs the heat from the surrounding, not from the liquid, not from the drink. So here I'm gonna add this. Initially, each cup is 0.5 kg. Alright, the coffee is at 75.5 degrees Celsius. So can you please calculate the heat released? Alright, calculate the heat released. I know it's 10 already, but let's finish up. I think only left this and another question, then we are done for today. I have 2 answers already, 3 answers already. Four answers coming in. Okay, I'm gonna wait for another 30 seconds before I close and then I'll discuss the answer straight lah. So if you want me to discuss your answer, you better hurry up. I did kind of tell 4 Omega kids' parents, alright, during open day the other time. This 3 weeks of holiday in December is not a holiday at all. It's supposed to be preparing for your other half of your exam. So yeah lah, not only holiday for you, I also don't have holiday, okay? So I teman you. But I won't disturb your Christmas, don't worry. Okay, so I'm gonna stop the submission already in 5, 4, 3, 2, 1. Okay, no one sending in already. Okay. So over here, I'm gonna show you my working first. Sure to preface, huh? I don't know if what I did makes sense. Okay. Alright, so just now, let's see. The mass is 0.5 kg, initial temperature is 75.5 degrees Celsius. 0.5, 75.5. So the mass is 0.5 kg, initial temperature is 75.5 degrees Celsius. Coffee is cooled down to 25 degrees Celsius. Theta 2. Ray, that's why I opened the picture just now. 25 degrees Celsius. Specific heat capacity of coffee is 4,500 joules. So this specific heat capacity, you see the C over here? Okay, so specific heat capacity C is 4,500 joule per kg per degree Celsius. The main reason why I list everything out so I can see that the units are all in SI units except for temperature, okay? So I have M, I have change in temperature, I have C, so obviously I have to use Q equals to MC theta. For information, this is a past year question that I'm showing you. So you notice that the calculation is not very difficult. So the mass is 0.5, specific heat capacity is 4,500, change in temperature 75.5 minus 25. Okay, this one I think I can use my handphone calculator for a while. So that is 0.5 times 4500. So I have 2250 multiplied by multiply by 75.5 minus 25. So that is 50.5. Now you know why I always don't jump step. 2250 times 50.5. So the answer is 113625 joule. Alright, I can simplify my answer to be 113.6 kilojoule. I can also write the answer as 1.14 times 10 to the power of 5 joules. Whichever answer I will still accept. So let's see. This is normally a 2-mark question. I need to see the substitution and I need to see the final answer with the unit. Okay, so let's check. 1.14 times 10 to the power of 5. Okay.
Cher,
So
I
I
changed my answer. I did 4,200, Cher. It's supposed to be 4,500. So I changed my
so
answer.
in this case, you don't get a mark here, you know. So this is wrong and this is wrong already, you know. How to
Cher,
change answer in exam, Rabika?
Cher, please.
In exam, please be careful, eh?
Okay, okay.
Alright, here, alright, Lionel. Okay, correct, good. Both get 2 marks. And then here, Ray, let's see, Ray Masalah, the mess. So here, terus kosong already. I won't be able to give the marks for this. Okay, so the main reason is the main reason is because according to Puan Liao, our pencerama for the Form 5 previously, she did mention that if the formula is given in page 2, then the marks is not given for the formula. So the marks is given for the substitution. So, but do write it, continue practice to write the formulas anyhow. So Ray, sorry, kosong, uh, Li Sheng, MC Tita. Okay, Li Sheng, if you write like this, I can give you 1 mark only for the answer and unit. But your substitution, because you do not write your working, so you don't get the mark for substitution. Okay? Alright, so here Xin Yan, okay, 0.5. Dun 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 dun. Okay, good. This is 2 marks. Alright. Any other workings? Got. Okay. Working is here. Ada. Okay, 2 markah. Why am I speaking in BM? Uh, Even though no marks for formula, but Xingming, can I see formula? MC change of temperature. Okay. So, okay. Alright, so let's see. Okay. Last question. Last question. Calculate the mass of ice needed to cool the coffee in cup A to 25 degrees Celsius, assuming all the ice in cup A melted. Here the mass is still 0.5 kg, yeah? The mass is still 0.5 kg. The initial temperature 75.5 degrees Celsius. Those yang tak boleh tahan already up to you whether you want to leave or not lah, ha? But I'm going to finish up this question first. And I don't believe you guys sleep so early. I should just write out my answer working first. I'm showing you the initial question at the bottom. So the initial cup contains 0.5 kg of coffee. So the mass of 0.5 kg is for coffee. They ask you for the ice right now. Don't fall asleep, oh. And don't wait for the answers only. There's a reason why they give you specific heat capacity here. Right, I have answers coming in ready. I want to check the answer first. I got 3 answers already. Mm-hmm. Ray, you're working incomplete. Chinyan betul. Chong Wei, working incomplete. Xing Ming, working incomplete. Xing Ming, you got the idea already, actually. Lionel, good job. Okay, it's already 7 minutes. So I'm gonna wait until 8 minutes before I close the submission. Just to be fair to the rest of you who's still doing the question. 30 seconds to go.
Che, are you speaking? Your mic is off.
Okay, thank you, Rebecca. Now, okay, repeating again. This question is related to the question just now, whereby the coffee was initially cooled down from 75.5 degrees Celsius to 25 degrees Celsius. So the amount of heat that the coffee needs to absorb is actually 1.14 times 10 to the power of 6 joules. So we know that the heat absorbed by the coffee is being released by the ice. Okay, so and the question says that assume that all the ice in the cup A has already melted, and once it has already melted and it will reach 25 degrees Celsius, because the ice when it melts it will become water, and the water will actually mix with the coffee to reach the final temperature of 25 degrees Celsius, which means the amount of heat that is being absorbed by the coffee is equivalent to the heat that is being released by the ice. So the amount of heat energy that is being absorbed by the coffee was what we calculated just now, which is 1.14 times 10 to the power of 6 joules. But the amount of heat that is being released, it is actually from ice at 0 degrees Celsius. It needs to change to water at 0 degrees Celsius, and then the ice is fully melted and the coffee up to 25 degrees Celsius, which means that the ice that has changed to water will rise its temperature up to 25 degrees Celsius as well. So here we will need to use Q equals to ml and Q equals to mc theta here. And this m is the mass of the ice, the same mass of the ice. So here is mass of ice, specific latent heat L of fusion, plus mass of the ice, specific heat capacity of the water, and the change in temperature. So the mass of ice I take out, I have the latent heat plus heat capacity, specific heat capacity plus the change in temperature. So M bracket specific latent heat. Remember the L. The L shows its latent heat. The C stands for specific heat capacity, so that's the C. So here is 3.36 times 10 to the power of 5, close bracket, plus specific heat capacity is 4,200. Change in temperature 0 degrees to 25 degrees. So this is 25 degrees Celsius. So when you rearrange, you will get M equals to 0.26 kg. This is what I got lah. Okay. So this is actually the working. So let's go check. This is a 3-mark question. So 3-mark question, where does it come from? So obviously 1 mark would be here. To substitute the answer here, 1 mark. Over here, the 2nd mark, final answer with a unit, another mark. So I need to see this substitution actually. Okay, so Ray, I did mention just now, the working is incomplete because he only have Q equals to ml. So I can give 1 mark for here. All right, Ray, I only can give 1 mark from here, the one that you have calculated from the previous question. So only that 1 mark, the rest, tada. So Xinyan over here, she did exactly the same. She substituted from the previous question. She put in, Xinyan, be very careful. Oh. Okay? Please put the brackets over there. Alright, so substitution is there. So the other mark, and then final answer with a unit, 1 mark, 3 marks here. Chong Wei, I would do one thing. When I see Chong Wei's this working, I will put a question mark and question mark here. I don't even know what he's doing. Okay? Apa ini? And then here I know it's M. This is this specific latent heat? So Chong Wei salah working. Okay, so here Xing Ming also incomplete. This one was calculated from previous, and then only here Q equals to ml. The MC theta is missing. Alright, so I can only give the substitution 1 mark here. Alright, Xing Ming, the rest is all wrong. Lionel, alright, so I saw the equation here. So the substitution 1 mark. Here also 1 mark. Lionel, be careful. Bracket, please. 25.5. Okay. Betul. Supposed to be 25.5. Alright. So answer unit correct. Lionel, 4 decimal places should be okay, but maximum 3 should be sufficient already, Lionel. Alright. Li Cheng over here. Here only got MC theta. Li Cheng, this one is definitely wrong already. ML is not equivalent to MC theta here. Okay, so I can't even give you any substitution mark because I need to find the other one. Alright. So one last question. What is the assumption made? I think this one should be very fast for everyone. What is the assumption made? This is memang last question already. I already checked. All ice has melted. Heat of the coffee is not influenced by the surrounding temperature and only by the ice. Ice is melted by heat completely by the coffee. Ice is only absorbing the heat from the coffee. Darren betul, Lionel betul, Shinyan betul, Ray betul. I can accept all the answers. Any other answers that I need to consider? No heat from the coffee is released to the surrounding. Good, Rebecca. No transfer of heat from surrounding into the coffee. Okay. Can accept, Brian. Any other answers before I stop the submission? So far, I can accept all this answer. No already, ah? Okay, since 2 minutes. Xing Ming, no heat loss of ice to surrounding. Okay, can acceptable. Correct also. Alright, so I'm gonna stop the submission here. Chongwei, why do you always have to do something like this? Assuming my calculation is correct, ice is only absorbed when it is in the substance and not. Ice is only absorbed when it's in the substance and not outside, and no transfer of heat inside the coffee. Chongwei, I don't even know how to give you marks for this. I don't. Okay, in terms of question like this, right? Whether your top answer is correct or wrong, it is independent to the current assumption. Okay, Chongwei? Whether the top answer is correct or wrong, it is independent. This answer is independent. So your calculation can be all wrong, but if your assumption is correct, I'll still give you that 1 mark. Okay? But for Chongwei's answer, ice is only absorbed when it is in the substance and not outside. I have to think very, very long. And right now, I think my head also cannot think whether this answer is correct or wrong. So, Chongwei, I shall reply back to you later on. All right, so I'm going to stop the lesson here. I think this is one of the very, very the long timing already. Okay, so I'm going to stop the recording. So that's it for today's for specific Latin